In our last order of business today, we want to talk about the types of error that you encounter in chemical analysis. In terms of the nuts and bolts of our discussion of error, our discussion of error centers around all of Chapter 3 in Harris's Quantitative Chemical Analysis. And as we start to sprinkle statistical treatments into our error analysis, you should start on Chapter 4 as well. And we'll start on statistics formally at the end of the day on Friday this week. So your assigned reading for this week is all of Harris Chapter 3 and all of Harris Chapter 4. And at the conclusion of this module, I hope that you'll be able to pick up the following skills. You should be able to calculate relative error given the absolute error associated with a specific scientific measurement. I'd like you to be able to identify examples of error as one of the three general types of error: systematic, random, or gross error in an analytical measurement, and identify where likely sources of error might be if we talk about the context of making a measurement or the process of making a measurement. We're going to spend the bulk of the chapter talking about propagation of error, the mathematical process by which we judge the likely amount of error associated with a chemical measurement according to a specific procedure. And we'll talk about how to propagate quantitatively both random error and systematic error in laboratory experiments, and after looking at the series of measurements made in an experiment, make a quantitative determination of how much error is going to be associated with the final measurement. In terms of the new vocabulary for this chapter, I'd like you to pay particular attention to the interchangeable terms error and uncertainty and what they mean in a scientific context. We've previously introduced you to absolute and relative error when we talked about the glassware available to you in the analytical lab. We're going to introduce you to systematic, random, and gross error as our three main types of error today. And then we're going to spend the bulk of the chapter, as I said, talking about error propagation or propagation of error. So, as I mentioned in the context intro, the lead-in for this chapter, no analytical measurement is without error. Your job as an analyst is to make sure that avoidable sources of error in an experiment are minimized, both in how the experiment is designed. That won't be your guys' responsibility yet, because in lab, you'll get a set of specific instructions for how to do an analysis, but also how you use your tools to come up with the values that you come up with in lab is a possible source of error. So what we really want you to learn to refine this term, particularly in your lab work, is how to improve your technique and improve your use of standard laboratory equipment like volumetric pipettes, like burettes, like volumetric flasks, to minimize avoidable error in the execution of your experiments and really winnow that error down to the unavoidable random error that comes with making any measurement. And so the question that I'd like to address today is, where does error come from and what types of error are there? Well, the ultimate answer as to where does error comes from two places. The unavoidable error associated with the engineering that goes into your laboratory equipment. Error also comes from how an experiment is designed, and therefore what tools you're required to use to complete the experiment. And lastly, error comes from your experience and your skill acquisition as an analyst. The more quality practice you have with your laboratory instruments and the more you refine your technique, the less error there is associated with the values that you determine in any given experiment. So it's partially refining your skills as an analyst. It's partially down to the equipment that you have to use to complete your experiment. These are the two kind of fundamental sources of error. And within those kind of fundamental sources of error, analysts usually say that there are three basic types of error. There's what we call systematic or determinate error, there's random or indeterminate error, and there's gross error. Gross error we addressed a little bit in the context intro for this lecture module, where gross error is some type of failure of the analyst to... Gross error is an instance where an analyst has obviously and dramatically failed to execute a procedure correctly, or it's related to an inexperience with using the tools that you need to complete a specific experiment. It could be something like a spill in the lab or failure to, a bad failure to read a piece of equipment correctly. Therefore, you performed the reaction at the wrong temperature, or you had a leak in your pipette or your burette and you didn't notice it. These are all instances of gross error. Like I said in the previous lecture, one of your jobs as a young scientist is to get your technique up to the point where you can commit gross errors as infrequently as possible. Because when you commit a gross error during the procedure, you have to reject the data you got from that experiment, and you probably have to start again. So let's talk about the two remaining types. Let's talk systematic error and random error. So systematic, or what Harris calls determinate error, is a reproducible error which generally comes from instruments and equipment. Because systematic errors are reproducible, they can be controlled for. In the context of our class, we'll call out systematic errors for you, and systematic errors will be recognizable because you know the exact value of the error and whether the error is biased high or biased low. So we'll talk more about an example of that in a second, but in general, systematic errors arise from inaccurately calibrated equipment, the order of sample preparation during your experiment, the action of chemical interference in the matrix, and types of persistent contamination in a specific lab. So an example of systematic error usually has to do with the calibration of specific instruments or glassware throughout the lab. In your first week of lab work, you've been using a standard calibration procedure to try to determine the systematic error associated with using typical pieces of laboratory glassware like burettes or volumetric pipettes. Through calibration and careful experimentation, we can recognize and quantify systematic errors, and because systematic errors can be specifically associated with specific pieces of instrument or equipment around the lab, we can actually, through calibration, figure out how big the error is and account for it, and thus remove the systematic error from the procedure. So a specific example of systematic error would be if you have a pH probe and you calibrate it using a series of buffers at pH 4, 7, and 10, so that it will take accurate pH readings. If you calibrate it incorrectly at, say, pH 7, and you calibrate it to a buffer whose pH has slipped from 7 to 7.08, the pH probe will associate a current measurement that actually means pH of 7.08 with a pH of 7. And so as a result, you get a systematic error where if you use that probe that's been calibrated incorrectly, anytime you're measuring near pH 7, that probe will read 0.08 pH units too low. And so when you think you have a pH of 7, you would actually have a pH of 6.92. With a systematic error, we know the magnitude of the error and we know whether it's biased high or biased low, so we can apply a correction procedure, which is either a recalibration of the equipment or a correction factor by which we adjust the values that we're getting to account for the systematic error, and thus we can cancel out the effect of those systematic errors. Anything that's associated with miscalibrated instrumentation or lab equipment counts as a systematic error and can be corrected through calibration. Random error, or what Harris calls indeterminate error, is a little more pernicious and harder to account for. Random error arises from our inability to measure the same quantity with perfect consistency due to natural fluctuations in the environment. And so random error covers things that can't be fixed through calibration. Random errors can be minimized by improving your laboratory technique or watching reaction conditions a little more closely. But random error is always irreproducible and difficult to control for. So in certain situations, random error can be minimized, but it can never be removed entirely from an experiment. Systematic error can more or less entirely be removed from an experiment, where random error effects can only be minimized. So for instance, we can see random error in action in a very simple example. Let's say I give you a representation of a dollar bill. This dollar bill is not actual size, not quite, but it is to scale with the ruler that I've drawn under it. Take a second, just like 5 seconds, and see what you think the length of this dollar bill is in centimeters. I've drawn a line on the ruler to try to help you out. Now you probably came up with a good answer for the length of that dollar bill, but it might surprise you to learn that if everyone in class made that same determination as to the length of the dollar bill, we would get subtly different numbers from everybody. In a class of around 18 students like we are, we would probably get at least 5 or 6 slightly different measurements for the length of that dollar bill. And that's down to the fact that in the ruler that I've given you, the tick marks are at only half a centimeter. So you have to interpolate or quantitatively estimate where the edge of that dollar bill actually is between the 15.5 centimeter and the 16 centimeter mark. And so making that quantitative estimate as to where the line falls in between 15.5 and 16 requires you to estimate a little bit, and this introduces random error. So random error springs up whenever you're measuring something by eye, trying to read a meniscus level by eye, for instance. It can arise from random fluctuations in pressure or temperature during the course of an experiment that's open to the atmosphere. Or if you're doing an instrumental experiment, the fluctuations of electrons at room temperature inside the wires of the electronics in the instrument actually contribute to the signal that you're getting from the instrument. So it introduces some noise, a little bit of oscillation to the signal, which can change your values a little bit. All these situations are unavoidable. By understanding our instruments better, or the setup of our reaction, or practicing reading a meniscus, we can minimize the random error, but we can never remove it entirely. So these are your 3 types of fundamental error in a chemical analysis: systematic, random, and gross error. When we come back tomorrow, we'll talk more about how we quantify error and how we can use error in individual measurements that we make during an experiment to get a good quantitative estimate to propagate the error in the ultimate result that we're interested in. Let me know if you have any questions on Zoom today. Otherwise, I'll see you on Wednesday.